Good evening and welcome, everybody. On behalf of the Tata Institute of Fundamental Research, I would like to extend this warm welcome to you for the public lecture by distinguished mathematician Professor Etienne Ghys from the École Normale Supérieure Lyon in France. And this public lecture is an event of the National Mathematics Year, celebrating the 125th birth anniversary of Ramanujan. It is being organized jointly by the Ramanujan Mathematics Society, the School of Mathematics of TIFR, and the International Center for Theoretical Sciences of TIFR. I'd like to just mention that this is the third mathematics public lecture since the beginning of this year, the previous two being delivered by Benedict Ross and Terence Tao. And in May, we will have another one by Peter Sarnak. I'm very happy about this development, as I think that it is crucial on many accounts to have a strong mathematics outreach program, not only because the laws of nature have a precise formulation in terms of the language of mathematics, but also because mathematics has an internal and independent structure of great beauty and power. So I think it's important to partake in beautiful things. And with these few words, I'd like to invite Professor M.S. Narasimhan to say a few words on this occasion, and after that, present flowers and a memento to Professor Ghys. Professor Narasimhan.
Good evening. I'm very happy to introduce Professor Etienne Ghys. Professor Ghys is Director of the Research in CNRS. CNRS, as you know, is the French National Center for Scientific Research. It's a premier scientific organization in France. And he works at École Normale Supérieure at Lyon. He is a member of the French Academy of Sciences, and he has also received various other honors and awards, like the D'Alembert Medal of the French Mathematical Society. His mathematical interests are broad and focuses mainly, though, on geometry and dynamical systems. He is also very much interested in the historical development of ideas in mathematics rather than just only history of mathematics, and especially in the contributions of Poincaré. That's one of his main interests in the study of historical development of ideas in mathematics. Actually, a recent outcome of his interest in the work of Poincaré is a beautiful book, surely written under his initiative, on uniformization theorem. So this book, it's written in French. I'm sure it will be translated someday in English. But for those who can read French, I really recommend that book. It's really very enjoyable to read this book. And in the French tradition, which you are used to these days, for some time, this book is written by a group of French mathematicians under a pseudonym. This time only they have a new idea. The pseudonym, the first names of the pseudonyms are Henri and Paul, which is supposed to be Henri Poincaré and Paul Coupe. So that was the idea. And no, it's not only there's a kind of small puzzles you have to solve here and there, but it's a wonderful book. And I'm sure it is written under this initiative, though it's not mentioned there explicitly, I'm quite sure of this. Professor Ghys is a brilliant and inspiring lecturer of mathematics at various levels. On the one hand, he could give an excellent lecture and exposition on sophisticated ideas in mathematics to an audience of professional mathematician students. And on the other hand, he could also convey ideas of mathematics and also his excitement to a general public. Actually, as a part of his activity in popularizing mathematics, he has co-produced and also written, I suppose, part of it, a mathematical movie using computer graphics, focusing on spatial geometry and concept of dimension to introduce to general public the idea of dimension mainly, I suppose, was the final aim, but done in stages. So I am very glad that he has agreed to give this public lecture here and also come and give the excellent lectures which he's giving at more professional, more technical level, and I welcome him again.
Thank you, Professor Narasimhan. May I now request Professor Dani to come and say a few words about the occasion.
Good afternoon, everyone. I am very pleased to welcome you on this occasion. We may be going somewhat in an incorrect order, in the sense that Professor Narasimhan has kindly introduced the speaker to you in substantial detail. So I will not want to try to add anything and take your time on that. But I think it's probably worthwhile for me to say a few words about how he happens to be here, the occasion or the reason which brings him here. As you would all know, that this is the 125th birth centenary year of Srinivasa Ramanujan. He was born in 1887, and now we are in the 125th year. You would also know that the community, mathematical community as a whole, is now blessed on this on account of this with the National Mathematics Year. The Prime Minister announced this on 26th December, which many of you, I am sure, you would know. So Ramanujan was born on 22nd December, so 22nd December to 22nd December of 2012, which might actually spill over. The years of this kind usually are not limited to 365 days, but do tend to spill over. So it's going to be the National Mathematics Year. Now, often people ask me, what does it mean? What is the provision? Of course, what is meant is to convey a certain sense of importance to be associated to mathematics and take from there at all levels. It's not necessarily that only the government is going to start programs for this. The idea is to galvanize the mathematical community and all those who are in one way or other connected with that into taking a step forward in recognizing our own mathematical potential or create our own activities and so on. And though I'll not go into the details, I must say many agencies have taken this in the correct spirit, and many programs are being mooted at various levels, at various institutions and so on. So, in fact, sometimes some of the conferences, etc., which were actually being proposed to be held in 2013 have been preponed to sort of make it a part of the National Mathematics Year. This is only a kind of side thing. So, but there is a kind of a lot of enthusiasm in doing one's own thing at various levels to fulfill the objectives of the year. Now, one of the major institutions which has actually been involved is the Ramanujan Mathematical Society, and in fact, to a large extent, the fact of this year coming into being itself has to do with the Ramanujan Mathematical Society, and as you would know, it is our eminent colleague, a former colleague and eminent mathematician, Professor M.S. Raghunathan, who is the president of the Ramanujan Mathematical Society, and he has been the inspiration and guiding spirit for a variety of activities in as a part of the year. There's a whole gamut of programs that are proposed. I will not go into too many details, but as a part of that, one of the programs that was proposed and has been supported through government funding is the Panorama Lectures. It's something called the Panorama Lectures. There's a committee set up to draw up a list of eminent mathematicians from around the world, and so that they could be invited to spend time in India, at least 1 week, with an intense activity at a suitable center, where they could give an exposition into an emerging advanced area to people at various levels, including research scholars and so on, which as you would see, has a great potential of developing new areas, developing strength in mathematics, and a host of other advantages, young people getting inspired by the presence of the eminent people. And I'm happy to say that Professor Etienne Ghys, today's speaker, is one of the people who featured in the list that was drawn up by the committee, and he also kindly agreed to be with us. He has been giving these panorama lectures during this week, 9 to 14. Initially, the plan was there will be 8 or 10 lectures, which have happened. Tomorrow there is going to be the last lecture. But in addition to that, he also introduced the exercise sessions and has been interacting so thoroughly with the students that I think we have got more than what we actually looked for or bargained for. I mean, so he has been such a enthusiastic teacher, and expositor of Professor Narasimhan already mentioned that his qualities at exposition, and that actually is the case at various levels. I mean, he has written many expository articles in this seminar Bourbaki, which usually gives topical expositions, where the major results, which are usually understood only by 1 or 2 people or 2 or 3 few people, are given exposition by a third person, and very often Professor Ghys has undertaken to do that. This is exposition from the source of the scholarly of the major discoveries to a wider community. Then he has also worked on given lectures at a variety of places to students at various levels, and then he has also been played an important role in outreach. Now, I do not know how many of you had the opportunity of listening to his previous talk in this very same hall in December 2007. I am sure those of you who could be there would actually remember the spirit and even perhaps the talk. I mean, I don't know, I should not anticipate. So it really has. It's a good fortune that he's here yet again. This is actually his 3rd visit at the Tata Institute and 4th visit to India, and I do hope he keeps coming and helping us in promoting mathematics. I'll just take continuing with my previous theme, let me also mention a couple of programs of the Ramanujan proposed by the Ramanujan Mathematical Society as a part of this mathematics year. There is a program to translate many important books from English to some of the regional languages, so that for the students do not always have to depend on the sources in English to get the inspiration. Of course, once they have the inspiration to go into mathematics, of course, it's important to know the language. But the translations would have a potential of encouraging students into getting into mathematics. There's also a plan mooted to bring up a mathematics museum. And that will again have its own inspirational value in various respects. So, and again, the society, Ramanujan Mathematical Society and Professor Raghunathan in particular has been pursuing it energetically, and let's all hope that it takes us much further in the coming years. So, yeah, with these few words, I think I'll invite Professor Ghys to give his talk.
Thank you very much for these very kind words. I'm very honored by your hospitality. This evening, I would like to tell you about a story that occurred to me some time ago. I had the opportunity somehow to meet indirectly a mathematician. This mathematician, I will introduce him to you, has a very strange first name. Pafnuti. I think he's the only man on this planet with this first name. His name is famous in mathematics. He's Chebyshev. There is different spellings depending on the way you write it in French or in English or in Russian, of course. He was born in 1821 and he passed away in 1894. And I would like to introduce him to you to show how great he was, how he had a unified view on mathematics, and how he was able to think and do things in mathematics in all possible directions. So before I go to my main part of my talk, which is really the story that happened to me, and which is, of course, as you can guess from the title, related to geometry, I want quickly to give you a quick overview of the contribution of Chebyshev to mathematics. So here's his portrait. He looks serious. Here is a few fields that he looked at: probability, number theory, analysis, and geometry. You can almost say that he did everything. So before I go to geometry, which is the part of the discussion of today, I want to give you some ideas of what he did in probability, in number theory, analysis. Probability, he's the first one who proved the law of large numbers. Up to then, people had a rough idea about probability. They didn't state a theorem about it. If you throw a coin and you wait a long time, you will think that half the time, basically, it will be on one side, and half the time it will be on the other side. So you expect that the probability will go to 50%. We all think this is true, but this requires a proof. And Chebyshev was the first one to prove it. This is the paper. You see it's a theorem. And by the way, you can see that he was writing papers in French. Good old times. Number theory. He is the first one, not the last one, who said and proved a theorem about the distribution of prime numbers. So basically, he proved that if you take a large number and if you compute how many numbers smaller than n are prime, then the probability is about 1 over log n. So for example, if you take n is equal to 10 to the 10, it turns out that there are 404,204,997 prime numbers, which gives a proportion like that, which is not so far from 1 over log 10 to the 10. And he proved that the proportion of prime numbers when n is big is close to 1 over log n. Again, you see, this is number theory, but this is also related to probability. And then I go to analysis. Oh, this is the French paper on the proof of prime numbers. If you go to analysis, let me show this picture. This is a photograph of a reconstitution of his office in St. Petersburg. This office of Chebyshev does not really look like my office. It's full of gadgets. It's full of objects. You see, at the end of the 19th century, there was a strong need for applications of mathematics. There was this industrial revolution. Trains were crossing the continents. There was a need for machines, for understanding the energy and things like that. And you see here some funny gadgets, like for example, I will show you maybe later, one sees somewhere some prototype of a bicycle in wood. And many funny objects. But let me show you one of his inventions in analysis. This is related to what we call to the approximation theory. Maybe some of you have heard of Chebyshev polynomials. Chebyshev polynomials that we study in calculus books, they come from this problem. The problem is this. You have a wheel which is rotating, and you want to find a system of bars that transforms the rotation in a rectilinear motion. This is a very important technical problem. How do you transform a rotation in a translation? And then he invented this object. You see, it's a polygon with 7 segments. And if one of the points follows the circle, then the other point follows a curve which is not a straight line, but which is close to a straight line. This is approximation to a straight line. And then Chebyshev wanted to use it to find a machine that would mimic the motion of my foot when I walk. You see, my foot is basically following the ground, so it follows some kind of horizontal line, and then I lift my foot a little bit, and then again it's on the ground, etc., etc. So he wanted to find a machine that was walking. So let me show you a modern reconstitution of his machine. This is an interesting website by Nikolai Andreev. Look at that. So this is the gadget. You see it's rotating on the circle, and up you see this strange curve, which is almost like a foot. And if you add several of them, you have a walking machine. And then you can adapt it. I have seen that machine in a museum. And even I've seen such a machine made out of Lego. It's a very interesting object. So it's in this paper where Chebyshev constructs this walking machine. At the end of the paper, it's very interesting because he says, well, he's Russian. He was Russian. And you know, there is a lot of snow in Russia. So from time to time, the trains have difficulties because they slide on the tracks. So Chebyshev explains that maybe that could be an option for trains to put feet. so that then when they arrive during a storm of snow, maybe the driver could stop the wheels and use the feet. So can you imagine trains walking? This is a very interesting story. I showed that to a friend of mine, and he showed me a contemporary artist, a guy whose name is Theo Jansen. He's from Denmark, and he produced exactly the same thing as Chebyshev. I'm going to show you that in a second. So I wrote a letter to this artist saying, well, great, you found the same thing as Chebyshev. But he never answered me. So look at this construction. This is the creation of this artist, Theo Jansen. This motion is fully governed by the wind. You see, this is totally mechanical system. The wind is blowing and these beasts are walking. It's kind of scaring. And if you look in the web page of this artist, he gives the dimension of the legs that he found by approximations. And the dimensions given by Chebyshev are much more accurate and much better. This is an interesting object. Okay, that was what I call analysis, application of mathematics to actual and useful problems. And then I come to geometry and the story that happened to me. Long time ago, long time ago, I like to read old books. So I was used to have a look in the collected papers of Chebyshev. And in the collected papers of Chebyshev, there is a page that you can see here with a strange title on cutting cloth, sur la coupe des vêtements. And this is not a paper of Chebyshev. The editors say that Mr. Chebyshev gave a lecture in Paris in, when was that? In 28th of August, 1878, and that he gave a wonderful conference explaining how to cloth a surface. Unfortunately, the paper written by Chebyshev was just handwritten. It was a draft, and on the margin of the draft, Chebyshev had not written publish. So the editors felt that it was not their role to publish this draft. So for many years I was thinking, what could there be in this draft? And rather recently I was reading a PhD thesis in history of mathematics, and in a footnote, the lady was saying that she had seen the manuscript. So I sent a message to her saying, well, could you tell me where you found it? And she answered, honestly, quickly, she answered, I forgot. Somewhere in Russia. So I was puzzled by that. So I knew, you know, when you look for a solution of a problem, if you know there is a solution, it's much better. So I knew there was a solution. So I decided to find it. Fortunately, I have a former student who is Russian and very nice, and he began a long query, and finally he found it in a box in the undergrounds of the Academy of Sciences in St. Petersburg. So I had this manuscript. I'm going to show it to you. This is Sur la coupe des habits. It's written in French again, rather good French, not too many mistakes. It's about 50 pages, handwritten in a pupil exercise book. And it contains equations and theorems and you know, formulas in the margin. This formula, which is here, we will see it again in a second. And sometimes he makes mistakes, and this is really a draft. And then let me tell you what he's doing. So I was really excited by this paper. I read it. I was impressed by the content of this paper. And I said to myself, I want to understand it, and if possible, I'd like to improve it, since I have more tools to study this kind of problems. So let me tell you what is the problem. The problem is the following. You are given a piece of cloth, and you want to cut some shape that such a way that you can apply it to some surface, like for example my shoulder. Is it possible or not to clothe a surface? This is a very natural and useful problem. Of course, mathematicians have not, humanity has not waited for mathematicians to solve it. But anyway, this is a very natural question. So how do we formalize the problem? In the following way. You know, when you produce a cloth, you have two families of threads. You have this vertical family of threads and some horizontal families of threads, and they form little squares. So I looked in the English dictionary, there is a word for these threads. This is, I forgot, warp and weft. The warp is these vertical lines, and the weft is these horizontal lines. So when you prepare a piece of cloth, it is made out of two families, warp and weft. And when you deform it to deposit it on a surface, like my shoulder, what's happening? These threads become curves. Instead of being straight lines, they become curves. And so the main problem is this. When you deposit a piece of cloth on a surface, the little squares made by these threads, warp and weft, when they are deformed, the length of the sides is preserved because it's some kind of rigid thread, but the angles between them is allowed to change. So the little squares in the cloth, they can become rhombuses. Now we have a very precise mathematical problem. The mathematical problem is this. Definition, since we are mathematicians, we need definitions. A surface will be called clothable if it's possible to draw on it two families of threads in such a way that at the infinitesimal level, these little meshes are rhombuses. So this is a very natural question. I give you a surface, please find a clothing for it. Is it possible? Let me give a second definition, which is very different. Suppose that instead of trying to cover a surface with a cloth, I want to cover it with paper. Paper is more rigid. You cannot, if you draw on a sheet of paper two perpendicular lines, when you take your sheet of paper, the perpendicular remain perpendicular. So I will say that a surface is flat if it can be covered by two families of threads which form infinitesimal squares. So flat means essentially surfaces which can be covered with paper without creating folds or wrinkles. So let me ask you, which surfaces can be covered with paper? It is kind of clear that if I try to cover a sphere, for example, with paper, I cannot do it. There will be wrinkles or folding points, etc., etc. So what are the surfaces that can be covered with paper? This is a very, very old problem, going back to the 18th century, and I'm going to give you the solution that, of course, Chebyshev knew. Here's an example. you know, this kind of surface, of course you can put paper on it without creating folds. Can you find more examples? Can you imagine more examples of surfaces that can be covered with paper? Here's another example. Or another example, you take this, you glue the sides, and you get a hat. Can you find more complicated examples? And the answer is yes. There are more surfaces that can be covered with paper like that. And these surfaces have been studied and discovered by Euler. So let me show you two theorems. Theorem of Euler and Monge. If it is possible to cover a surface with paper, this surface has to be ruled. I should tell you what ruled means. A surface is ruled if it is obtained by a line which is moving in space. You take a straight line, you let it move in space, then this line will sweep a surface. Such a surface is called ruled. Now, look carefully. I didn't say that ruled surfaces are flat. I said flat surfaces are ruled. So here's an example. Before I go, and then I have to tell you what surfaces are flat. A surface is flat if and only if it is developable. Let me explain the words by pictures. This is a ruled surface. It's an hyperboloid. You see that this surface is obtained by straight lines moving. This surface is covered by straight lines. It's ruled surface. Is it flat? No. I mean, you can see that if I tried to cover that with paper, I couldn't succeed. So this surface, even though it is ruled, is not flat. Here's a flat surface. You take, you know, this curve in space. It's like a knot in a wire, and you let it roll on the ground. It will roll on a surface that you can see here in white, and of course this surface is flat because you can develop it on the ground. So that's one example. Here's another example. This is a beautiful developable surface, a flat surface. You can easily put paper on it, there will be no fold. So how is it done? The structure is this. You can see here, there is a curve. This is an interesting curve. And the recipe is the following. You take a curve in space, any curve. And for each point on the curve, you take its tangent. This gives you a family of lines which will sweep and develop a flat surface. And this is the theorem of Euler. A surface can be covered with paper with no fold if and only if it is obtained as the family of tangents to some curve in free space. This is a wonderful theorem, but I wanted to explain that to you to show you that most surfaces are not like that. Most surfaces cannot be covered with paper. We could guess it from the sphere case, but this is now a theorem. If a surface is not obtained by this very specific construction, then you cannot cover it with paper. Let me show you that this theory of developable and flat surfaces is not completely out of date. Let me show you one recent paper on developing surfaces. You see, they are trying to draw shoes. A shoe is made of leather, and of course the shape of the shoe is flat. So the question is, how do you do that in an efficient way? How do you cut the leather to produce shoes? And this paper gives you, developable surfaces from arbitrary sketch boundaries. This is numerical mathematics. It's non-trivial modern mathematics. Here's another example that you can see developable and flat surfaces. So this is just to tell you that this is not because a theorem has been proved by Euler that we should forget it. It's useful. Okay, so enough for surfaces covered with paper. Let's go to cloth. Which surfaces can be covered with cloth? So there is a theorem. This theorem is by Chebyshev in this draft, in this paper. Theorem is this: any surface whatsoever can always be covered locally by a piece of cloth. So what does that mean, locally? That means that if you have a complicated surface, if you give me a point on it, you can find a little neighborhood of it that you can cover with a cloth. But maybe you will need many pieces. The theorem is only a local theorem. A given surface may require hundreds of pieces of cloth to be covered properly. So this is already a non-trivial theorem. You're giving me any surface whatsoever, pick a point on it. It's always possible to find on it two families of threads, warp and weft, that make little rhombuses. In modern terminology, of course, the proof of Chebyshev is not complete. He's just guessing things. He's not able to do it because he's not mastering enough the modern technique that we know today. Because after all, this theorem is a theorem of partial differential equations of the so-called hyperbolic type. So today we can prove it easily, but in the time of Chebyshev it was not only difficult but almost impossible for him. But he guessed it. Let me give my proof. My proof is this. The hammock. If I put my body in a hammock, the hammock will take the form of my body. And if you look at the hammock, you see it is made out of little rhombuses that, of course, will remain rhombuses because the threads constituting the hammock are rigid, and the only possibility for them is that they are fixed at these knots. So when you deform it, the angles may change, but not the length. So if you put a net on the surface, sure, it will take the shape of the surface and it will clothe the surface locally. Of course, this is a discrete version of a cloth. The mathematical cloth is not one thread, another thread. It's just a family of threads. And what I said, I wanted infinitesimal rhombuses. So if you want to prove infinitesimally this theorem, you do need partial differential equations. Okay, so according to Chebyshev, we know that it is possible to clothe any surface locally. And then Chebyshev goes to a theorem, and this is the main theorem in this draft, in this unpublished manuscript of Chebyshev. He proves that it is possible to clothe half sphere and hemisphere. And taking two copies of it, you can clothe the sphere with two pieces of cloth. This is the main result of this paper. It is possible to clothe the sphere with two pieces of cloth, each one covering half of the sphere. Let me show you the picture. This is a picture from the paper of Chebyshev, or more precisely, in the box containing the exercise book. There was also this. This has been cut by Chebyshev. You see this shape, And the theorem of Chebyshev is this. You take your cloth, you put this shape on it, and you cut on the boundary. You get a piece of cloth. Now you take a ball, you put the midpoint on the top of the ball, and the cloth will go on the sphere. And the theorem is that the boundary of this shape will go exactly on the equator. And there will be no fold. It will be just perfect clothing. So if you take two copies of that, you can sew them on the boundary, and you have a closed sphere. So this is the main theorem in this paper. So I was really amazed by that, and as I told you, I wanted to understand it, and if possible, to do something better. And I'm very happy because I can do something better than Chebyshev. I can prove the following theorem. It's possible to close the sphere with only one piece of cloth. And I'm going to show it to you. Here's my template. Look at that. If you cut a piece of cloth with this shape, I claim that it can be used to clothe a sphere. So on this picture, I did not draw the warp and weft. The warp and weft are the warp are vertical lines, and the weft are horizontal lines. What I did draw was these curves. You see, the midpoint will go to the north pole of my sphere, and these red closed curves, when I deposit them on the sphere, go to the parallels of my sphere. The blue, the thick blue curve goes to the equator, and the larger blue go to parallels, which are closer to the South Pole, and the four endpoints go to the South Pole. Moreover, I drew, starting from the origin in red, I drew the curves that are mapped to the longitudes. So you take this star-shaped object and you fold it on the sphere. You will see it better in a moment. And the theorem is that this is perfect clothing. So let me show you how it works. This is a template. Now you take the ball, and I'm going to wrap it in the template. And you can see that at each moment, the little squares are rhombuses. So the lower half is the theorem of Chebyshev. So to speak, Chebyshev was not courageous enough to go to the South Pole. Look, I like this picture. I was told that I should patent it. Maybe for Nike or something, or for tennis balls or something like that. Okay, so how can one prove that? Of course, today I don't want to go into any kind of technical details. I just want to give you some insight of what kind of problems we meet and why this is really interesting, because it was a way of connecting old mathematics with new mathematics. So here's an equation that one finds in the draft. The equation is the following. Suppose you have a piece of cloth lying on a surface. Well, at each point, xy, the two threads make some angle, omega. So you have a function omega of x and y. And the paper of Chebyshev tells you how to compute the curvature of the surface as how it depends on the function omega xy. And the formula is simply this one. K is the curvature, sine is just the sinus, omega is the angle, and this is just the partial derivative, second partial derivative with respect to x and y. So this is a simple formula, which enables you to compute the curvature of a closed surface. It just takes second derivative of the angle as respect to x and then respect to y, and you get the curvature. This is not so hard. This is in page 1 or 2 of the draft of Chebyshev. If we want to close the sphere, well, the sphere has curvature 1, constant. So what you do is that you replace k by 1, and you get d2 omega dx dy is minus sine omega. Miracle. This is a partial differential equation that all physicists, or many physicists, know. This is the so-called sine-Gordon equation, which has been discovered and studied much, much later. So the sine-Gordon equation is very famous in physics because it's the prototype of differential equation that admits solitary waves. I will show you that in a second. This is something really fundamental that has been discovered in the 20th century. But now you can see that in the draft of Chebyshev, this equation was already there. So there is a connection between clothing surfaces and solitons and clothing surfaces. Let me show you why this differential equation is well known among physicists. It comes from this kind of phenomenon. You have a family of a sequence of pendulums, and each one is just oscillating this way, but each one is influencing its two neighbors. So this produces a motion, and it turns out that this motion has some strange property that some waves can travel along the line of pendulums, and this is something very important in physics. I just want to show you by in practice how it is. Look, this is on YouTube. You see this strange behavior of these penduli. And okay, so I just wanted to tell you that this differential equation that is in Chebyshev's paper, 1878, turned out to be connected to contemporary physics. Okay, so what Chebyshev is doing is looking for a solution of this differential equation. This is the function omega xy is a function that you don't know. It's a function of two variables. And the equation is a so-called partial differential equation, which is a complicated differential equation. So what Chebyshev does is that let's look for a simple solution. And he says, let me look for a solution which is such that the angle omega of two variable xy is only a function of the product of the two coordinates. If you can do that, you find a function of one variable, and you may be in better shape. So if you replace in the differential equation that I wrote before, what you get is now a so-called ordinary differential equation with one variable, much easier, but still complicated. It's a nonlinear differential equation. And then Chebyshev says, okay, let me look for some approximation of the solution, and he looks for that. He looks for a solution to the third order. He does it, and then he stops. For him, that's enough. He doesn't prove the existence of the solution. He doesn't prove the existence of his clothing of the sphere. This approximation is good enough for him. He's an applied mathematician. He wants to solve the problem. He's not really interested by the proof of the theorem. Now, using my computer, which is here, I could do the same computation as Chebyshev, and I get that. It's a series that you can really prove that it is converging, and this is really the solution that Chebyshev was claiming. It does exist. He was right. No problem. The proof of Chebyshev is completely correct. Now, when I saw that, you know, since I am a mathematician of 2012, I know things that Chebyshev did not know, of course. In particular, I know that geometry, classical Euclidean geometry, has been generalized at the end of the 19th century by the non-Euclidean geometry. And that the sphere, which has curvature +1, has some kind of friend, which is the so-called non-Euclidean plane, which has curvature -1. And this non-Euclidean plane, I will say a little bit about it, this non-Euclidean plane is the locus where most of us do geometry today. This is non-Euclidean geometry. And of course, for me, when I see a sphere, immediately I think of the non-Euclidean plane of curvature -1. So my immediate reaction was, why not changing a sign in the equation of sine-Gordon, just to see if I can clothe not the sphere, but the non-Euclidean plane. And I could do it. Let me show you that. First of all, a quick introduction to non-Euclidean plane. You see this disk, and you imagine that you live inside the disk, and you imagine that as you approach the boundary, for some reason, you shrink. Maybe, for example, there is a change of temperature, and you get smaller, and you shrink, you shrink, you shrink. You shrink so much that it's impossible for you to reach the boundary, because each time you try to reach it, you are twice as small, and you never reach it. So you have this kind of picture. You see this disk, which is full of butterflies, and you see these butterflies are smaller and smaller as you go to the boundary. So you have an infinite number of butterflies captured in the inside of this disk. So people living in the disk have a different geometry. They don't know that they shrink, but they have a different geometry. This is the so-called non-Euclidean geometry. And believe me, this has curvature -1. So here's another example with shells, and this is another picture which is more mathematical, which is related to what we call Fuchsian groups, and here's another example of Fuchsian group. So as you see, all these triangles, they look smaller and smaller, but for somebody living in the non-Euclidean geometry, they are the same, because they didn't notice that there was this shrinking process. So this is a bona fide geometry. We can live in it, we can do geometry, we can prove theorems, etc., etc. So it was for me a good question of knowing if it's possible to clothe it. Why not clothing the non-Euclidean geometry? And I did it, and I got that. You see, this is the disk, the non-Euclidean disk, and this is a domain. This is the domain that I can clothe. You can see the threads, the warp and weft. You see that there is a strong deformation, and that the rhombuses are more and more deformed in such a way that when you reach this line, the angle between the threads is 0. They became tangent. So you see, my clothing cannot extend beyond this line. So this is a clothing not of the full non-Euclidean plane, but of a part of it. And I was puzzled. Why am I unable to clothe the full non-Euclidean plane? And then I discovered that this is linked to another main problem of mathematics at the beginning of the 20th century. Hilbert, the great mathematician Hilbert, was really interested by the following question. Hilbert knew about this non-Euclidean geometry, this world inside a disk. But he was kind of puzzled by the idea that the objects could shrink when you reach the boundary. And he said, why not trying to realize a surface in 3 space, a usual space, in such a way that the geometry of that surface would be the geometry of the non-Euclidean plane. So he was looking for representation, embedding of the non-Euclidean plane in 3 space. And some people could do something. Like, for example, you have this surface, which is due to Beltrami, which has the geometry of the non-Euclidean plane, but which unfortunately is only a part of it. You can see here this line that we call a singular line. This singular line is a bad line, which implies in particular that it does not represent the full non-Euclidean plane. It's just a part of it. And then people were trying to find other surfaces. Here's another one due to Dini. But always, 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 there was this singular line that people cannot avoid. And then Hilbert came, and he proved that these singular lines have to be there because it is impossible to embed the non-Euclidean plane in 3 space. And the miracle that I found fascinating is that Hilbert, not knowing about Chebyshev, rediscovered clothing of surfaces. So let me explain what what Hilbert did. This is a proposition of Hilbert, which is really, I think, fascinating. Hilbert, without having read, of course it was in a box in St. Petersburg, found again this concept of clothing of surfaces, and he used it to prove that it's not possible to represent non-Euclidean geometry in 3 space. So he proved the following theorem. I'm going to explain that to you. He said asymptotic lines on a surface of curvature -1 define a Chebyshev net. Let me explain what this means. Here's a surface. I assume this surface has a saddle shape. Pick a point on it and look at the tangent plane, the red tangent plane. This red tangent plane intersects the surface on 2 lines whose tangents give you 2 directions. The conclusion is that each time you have a surface in 3 space, which is saddle-shaped in each point, you have 2 directions everywhere. And these 2 directions will give you 2 families of threads. Usually, these 2 families of threads do not define the clothing. There is no reason to believe that the infinitesimal things are rhombuses. But Hilbert proves that this is a clothing if and only if the curvature is -1. If and only if it is non-Euclidean geometry. So non-Euclidean geometry is exactly the same thing as surfaces in 3 space clothed by the asymptotic lines. So I think I like it very much because it's a connection between a very practical question, how to clothe surfaces, something very practical, and a theoretical question, how to represent the non-Euclidean geometry in space. And then Hilbert was able to prove this wonderful theorem. It is impossible to embed the non-Euclidean plane in Euclidean space. This is one of the most beautiful, Hilbert proved many beautiful theorems, but this is one of them. And the proof of Hilbert uses directly the theorem of Chebyshev that he didn't know about. Now, I told you that I was able, using the techniques of Chebyshev, to clothe part of the non-Euclidean plane. I showed you this picture with this star-shaped thing in the non-Euclidean plane. And then this enabled me to embed in 3 space part of the non-Euclidean plane. And I found a surface. I wrote nu between quotes because during a few months I was convinced I was the inventor of this surface. I was very happy with that. And recently I discovered that it's not new. Somebody found it in 1956. Somebody called Hamsler. He found the same surface, and he didn't draw any picture of it. He gave formulas. And I wanted to make a remark about that. I remember that a long time ago when I was a student, as you know, as any mathematician, it happens to you frequently that you prove a theorem and then later on you discover that somebody else did it. And then a long time ago I felt ashamed or unhappy with that. you discover that you did something and somebody else did it before you, I was unhappy. But maybe I'm getting older. But when I discovered that this surface I had discovered was not new, I was somehow happy. Because I had a feeling of, this kind of continuity of mathematics, from Chebyshev, Hilbert, Amsler, myself, like a long chain. And really, I like this feeling of belonging to some community. So let me show you some picture of this surface that I like very much, and let me show you even a film. So I'm going to show you the clothing of, I wanted to say my surface, clothing of my former, so I show you this. You will see the surface. I will pick a point on it. I will take tangent plane, and you will see that the tangent plane does cut the surface in the direction of the threads. So this is a surface with 4 endpoints. You can see the warp and weft. And then I pick a point somewhere. I take the tangent plane. And the tangent plane in blue, you see, intersect the surface along lines which are tangent to the warp and weft, as Hilbert taught us. This surface, I like it. I'm saying that for experts, because this surface has infinite area, and I think this is the first embedded surface with -1 curvature known with infinite area. Okay, so all of these things I was rather happy. I like this story. And it turned out that I have a friend in Lyon. He's an artist, and I told him about everything. And he's not a mathematician, he's an artist. He studied mathematics a long time ago. He has no formal education in mathematics, but he's fascinated by ellipses, parabolas, hyperbolas, quadrics, etc. And his artistic inspiration comes from mathematics. So from time to time, I meet him and we have discussions about mathematics, etc. And I want, first of all, to introduce introduce him to you. So to give you an example of the things that he's doing, you see that he went to a village close to Lyon, and he decided that when you harvest, traditionally when you harvest, you use straight lines. And you put the hay, you put the hay just on a rectangular array, which is for him not fun. So he decided to put them on ellipses following the Kepler law. So it was the opportunity to deposit the hay on these ellipses with the same focus, and he deposited them in such a way that they satisfied the law of area. It was fun, and then it was a big fest, and they had the opportunity to drink the local wine, and it was a good moment. So this is what Pierre Gallet is doing. He is not a mathematician, but he likes ideas coming from mathematics. So when I met him, I told him about clothing the sphere. I gave him these surfaces that I showed you, and he told me, well, you're a pure mathematician. I want to make it. I want to see it in truth, not in formula. I want to make it. So first of all, he tried with this kind of metallic grid. You see this kind of flexible metallic grid. You put a ball in it and you try to wrap it. And you see it doesn't work properly because you have on the top, it's a mess. So if you start in the wrong way on the bottom of the sphere, you cannot do the beautiful clothing that I showed you before. On the top, immediately you develop what people from partial differential equations called singularities, shocks. This is typical from partial differential equations in the hyperbolic domain. Shocks appear. You see here these shocks. So he was not really happy with that. He made several attempts, and then he decided to create the ball in wood. So how do you produce a ball out of wood? So he did the following thing. You cut a family of concentric circles. You pile them to create a sphere. You glue them, of course. And then you have to smooth it. It's a lot of work. And then you get the ball. He made 6 or 7 balls like that, some small, some big. One of them is 1.5 meters wide. And then he decided to smooth it, and then he decided to draw the warp and weft on the sphere. So he asked me, would you please give me the coordinates, latitude and longitude of every intersection point? So I sent him a file containing for each intersection point the coordinates, so he could do that, and he could construct it. You know, using centimeters, he could construct it point by point. And then he decided to put metal in it. And then he spent a long time, you see, hard work. He was happy with that because it was related with his conception. You see this beautiful object, which is the clothed sphere that I described to you earlier. You can see here the singular locus that you could see corresponding to the 4 boundaries of the star shape that I showed you. And then, well, the work is not completely finished, actually, and he doesn't know what to do with that now. But he doesn't care. You know, just like we prove theorems, you don't know what to do with them. But that's what he did. When I came to his place another time, he told me, okay, it's good, you are a good mathematician, you can close the sphere, but please, could you close an egg? Can you close an ellipsoid? And I have to tell you that I don't know the solution to this problem. I have no idea if it's possible to close an ellipsoid which is not a sphere. I tried a lot. I have some ideas for proving it, but I have only special results. So here's a theorem. This is, I put it only to impress you. This is just a theorem saying that I don't know the solution. This theorem says that it is possible to wrap an ellipsoid by a plane, but unfortunately this theorem is useless because it will create folding lines, and this is no good. However, there is a special case where I'm rather happy with that. If the sphere, if the ellipsoid is round enough, that is, if the axes of the ellipsoids are almost equal, then I can prove it. So I was happy with that. I came to my friend, I said, well, I can prove the theorem that if the ellipsoid is sufficiently round, then it's possible to close it. And he said, what do you mean by sufficiently round? And I said, well, there is an epsilon such that, and then he couldn't believe me. He said, you are useless. And I am useless. And the truth is that this is the present status of the question. I am working on it. I try to close ellipsoids. I don't know how to do. So I show you the kind of differential equations that you have to solve if you want to close an ellipsoid. So this is a terrible equation. You see here you have x and y are just the coordinates on warp and weft, and u and v are the coordinates on the ellipsoid, and you have to see which point in the cloth you send on which point on the ellipsoid. So you're really looking for two functions u and v of x and y, and this is the horrible equation that has to be satisfied if you want that the rhombuses are rhombuses. And these horrible equations include this gamma I, j, k, which are even more terrible, and which are called the Christoffel symbols of the surface, that I don't want to write it down here because they are so complicated. So this is the kind of mathematics that you have to deal with if you want to solve the problem of my friend and if you want to close an ellipsoid. So I cannot do it. I tried numerical experiments to check if it seems reasonable or not. And indeed, I mean, these kind of pictures are solutions of numerical solutions of the equations I had to solve. These numerics seems to indicate that it is indeed possible to close an ellipsoid, but this is just intuition, no theorems behind that. So here's the present status. I don't know how to close an egg. Now, to finish, I want to tell you how my friend Pierre Gallet, how he was able to incorporate this kind of problems in his own creativity. So as I told you, he doesn't know too much mathematics, but he was really interested by this idea of wrapping things. I mean, he told me that many artists like to wrap things. And so he produced a lot of pictures, and he wanted to cover surfaces that are not really the same as mine. And I wanted to, this is, you know, interesting surfaces. And recently, I mean, when was that? Recently, he gave an exhibition on this idea of clothing with mathematical background. And he gave this exhibition under the name, this is a picture that he drew. This is using Photoshop. Huh? He is trying to use this closed surface to imagine what could be artistic sculptures in a city, for example. Maybe he will succeed doing that. And I wanted to finish by mentioning this exhibition that he did in Lyon. Unfortunately, almost nobody went to his exhibition. But he found a very beautiful name for this exhibition. You see the word mathematics, and the title of the exhibition was Imagine. And I think it was a wonderful title, and I want to thank you for your attention.
Take a few questions. I think we need the lights in the auditorium, please. Yeah.
What was the first name before Chebyshev? The very first line?
Pafnuti.
In what connection?
It is the first name. Pafnuti is his first name.
Oh, I see.
Pafnuti is the first name of Chebyshev.
Oh, okay, I missed the point. Thank you.
Any other question, comment? Yes.
Is there any connection with the hairy ball theorem? Yes. Yes, there is one. As you can see on the way I close the sphere, there are specific points where things are not regular. And this specific point has to be there because of the hairy ball theorem. So you're right, there must be a singular point. Good point, good point.
Are there different possible ways of clothing?
Are there what?
Could there be more than one way of clothing?
Yes, yes. Locally, there's an infinite dimensional way of clothing. If you allow me just a little bit of mathematics, it's just like a Riemann surface. Locally, you have holomorphic change, which is infinite dimensional. But when you go to the global picture, like the sphere, for example, it is conceivable, like a Riemann surface has a finite number of automorphisms, it is conceivable, but I don't know, that the clothing of the sphere might be unique, up to some rigid transformation, something like that. So we have this is why I'm interested in this. You have local flexibility, just like in Riemann surfaces, and probably global rigidity. But this I'm not sure. This is just analogy.
Well, I have one comment that these beautiful surfaces of curvature -1 you showed are very prominent in string theory, actually.
This one?
Yes, this is the anti de Sitter space that you drew of curvature -1, right?
Yes, but anti de Sitter space is not definitely positive. Is Lorentzian geometry, eh?
Exactly, exactly.
Yeah.
But these pictures are usually, in public lectures in string theory.
Okay, okay.
These pictures are sort of quite useful.
This kind of pictures, yeah,
yes,
yeah.
Exactly.
Yeah, sure. Sure, but Lorentzian geometry is different feature. No?
Yeah, that's right. But you can also discuss the Euclidean part of it, actually.
Yes, like a square.
One is this
yeah,
one.
sure.
So if there are no further questions, let me thank Professor Ghys for a brilliant talk. It's a beautiful talk. And there is tea in the cafeteria on the right-hand side outside, so you're all welcome. So beautiful.